you can't actually touch anything. Our atoms are not coming into contact with the things that we're touching. They're simply interacting with it over a distance. So the question I'm going to answer today is, why can't you actually touch anything? And the force responsible for all of this, the problem is the electromagnetic force. It's basically a force between two charged particles. It can either be attraction or repulsion depending on the forces. Like forces repel each other, so a positive and a positive push each other apart, and opposite charge, a negative and a positive, would attract each other. So where do these charges come from? They come from the atoms themselves. All atoms have positive protons in the nucleus and negative electrons floating around. Now, these particles can cause forces of attraction and repulsion, even within the same molecules. So here's two molecules of water. When they're too far apart, the protons in one, the positive parts of one, are attracting the negative parts of another, and they pull closer together. This is why water doesn't just spread out spontaneously. But at the same time, when the two molecules of water get too close to each other, the same charges inside the nucleus, the protons of one and the protons of another, are going to push these molecules apart. And when you multiply this times billions of molecules, what you get is a state of matter we call liquid water. And that's because all the molecules are basically wiggling and jiggling, jostling around, not getting too close to each other, but also not getting too far apart. None of them can escape. None of them can just drift away because their neighbors are pulling on them. That is, until one of them gets enough momentum, basically from heat, to break free. And as a result, we've got what's called evaporation. This molecule of water up here is now going to be a molecule of water vapor because it's gotten enough energy to break free of its neighbors. So heat is essentially a particle that's gained motion or momentum. Anyways, so why is it that we can't squish atoms together so that we are touching? I mean, as much force as I can apply, couldn't I essentially squish two atoms together and so that their nuclei are touching? That's where all the mass is. And the answer is, basically there's too much empty space and the forces are too strong for us to ever do that. Thinking about the empty space, if we had a grain of rice at the center of a football field to represent the nucleus, the amount of empty space of a grain of rice-sized nucleus would take up the entire space of a football stadium, so that our nearest electron would be floating around in the parking lot. So that's how much empty space there is in an atom. And all of the matter, all of the stuff that actually matters and has mass to it, is in the nucleus. So why can't we squash that together? Well, it takes a lot of pressure. There are actually places where nuclei can be squashed together. One of them is, for example, in our own sun. The enormous pressures inside of there, because of all the matter and the gravity, can actually squish atoms close together. Not quite touching all of the time, but it squishes the nuclei close enough together that protons can stick and fuse together. Another place where that happens, and it happens even on a bigger scale, is a neutron star. Neutron stars are really interesting. They're basically stars that have collapsed, and they spin around thousands of times per minute, and they're wicked dense. All the matter inside of an enormous star is basically squashed down to the size of a larger planet or something like that. And if we could take a teaspoon of this material, because it's got so many nuclei in such close proximity, a simple teaspoon would weigh as much as like a mountain. And if you had a cup of it, it would make, it would probably, you'd feel an attractive force because of its own gravity. So it's wicked dense stuff, very, very close nuclei, got rid of most of the empty space inside of the atom. But there's even a place that's denser yet, and that's what we call a black hole. In a black hole, the nuclei have been squashed so close together that they form a material so dense that it creates gravity that can trap even light. So that's even more dense than the neutron star. And just as to show you what I'm talking about, again, this drawing is way out of whack because I can't show the scale very well, but A nucleus is incredibly small, incredibly dense, and at the center of the atom. And most of the rest of the atom is empty space before where you've got the electrons floating around. And talking about what would it mean to actually touch something, well, considering that electrons practically have no matter to them, and all the matter is in the nucleus, to squish those nuclei down would require pressures provided by gigantic stars. And as soon as you start doing that, you create material which has density enough to make a perceptible gravity. So are we actually touching anything? No. We're simply getting close enough that our own atoms are moving a little bit. So for example, here's the atom of my hand, and here's the atom of the thing I'm touching. And when my hand gets close enough to it, it starts to, have a little bit of an invisible interaction, but there's still going to be a little bit of space in between everything that we touch.